Hey guys, hope you're all doing good and welcome to an interesting video. Now many of you might have been at carnivals where you're supposed to take a coin and throw it inside a box of water, right? Now there's a small cup inside and the aim is to take this coin and put it over there. And if you have done this, you know that it's pretty much impossible to do this. So we decided to make a video to investigate this. So we first start with the experimental phase. Here we have a glass tank and now we fill it with water. Once that is taken care of, we take slow motion cameras and place it in front of the water tank. And that's basically it. Turn on the lights, start recording and start dropping some coins. Now if you watch the slow motion video, it looks pretty interesting. Note that each and every time you drop a coin, it just completely goes to a new location. It is as if the coin has its own mind. But in reality, it doesn't. It just has its own parachute. Wait, parachute? Well, when I'm dropping the coin, notice how it actually entrains air and there is this air bubble that's attached to the coin. This is kind of like a parachute because air has lower density, and this is exactly the reason why it's very hard to predict where the coin is going to fall. As the coin travels through the water, the surface pressure that's acting on the coin is continuously going to change. Now you can integrate this pressure force and split it into three force components, Fx, Fy and Fz. Then you can just apply Newton's second law, F equal to ma, to figure out the position, velocity and acceleration of the coin as a function of time. That's pretty easy, right? Well, not really. The only way you can do this is if you know what force is acting on the coin at what point of time and space, and that's pretty hard. So now you might be wondering, hey, how do I trust you? Well, you don't have to trust me, you can trust computational fluid dynamics. So what we decided to do is run a simple computational study. We created a simple CAD model of a tank and a coin and we performed a multi-phase flow simulation, right? We need to do that because there are two phases, air and water. Oh, by the way, you need to do something called as fluid structure interaction, which is enabled in this case. The reason why you need this is quite simple. The coin interacts with the fluid and the fluid interacts with the coin. In order to get this process correctly, you need a fluid structure interaction model. Alright, so we ran the simulation and here are some results. So first of all, notice how the simulation results closely map what you see in real life. That's pretty amazing. You can see the bubble formation because of air entrainment, and as the coin comes down, you can see that the bubble separates from the coin, and at this exact point of time and orientation, whatever forces that acts on the coin is going to take it to the next time step. And in the next time step, new values of forces are going to be present, which is going to take the coin to a totally different new location. This process continues, and that is why the coin is found in a completely new location. Now on top of this, we have also colored the coin by the static pressure, right? Here you can see that the static pressure is continuously changing. If the static pressure on the coin is going to change, so is the force components. That means the story that I said earlier checks out fine. Alright, with that I would like to conclude this video and I hope you had fun. Hey, and by the way, we have a lot of cool courses related to computational fluid dynamics, finite element analysis and design. So if you are a mechanical, aerospace or automotive engineer, do check them out. Thank you. Bye.